Okay. So this is to test the microphone.
My name is Simon Lamb. I'm a scientist.
Now,
In fact, I'm a geologist. I'm also a keen amateur cameraman.
So this is the crew. One cameraman, one chap roped in to do the sound. He happened to be walking past the door and looking like a complete idiot.
Lately, I've noticed something odd happening in the world of science. For the first time in my lifetime, scientists are under attack.
It's junk science, and it is a part of a massive international scientific fraud.
There is no scientific basis whatsoever.
This is a fraud and a scam and a hoax.
This ridiculous nonsense that man-made CO2 is causing global warming.
These extremists, these alarmists, are always finding something wrong.
These extremists and alarmists are, of course, scientists studying the climate. Could these accusations be true? Were dishonest climate scientists bringing all of us into disrepute? As a scientist, I had to find out.
I have to get my glasses.
So I decided to make a film about the scientists at the center of all this controversy. It took me to the ends of the earth and underneath it.
So, Mark, where are we now?
We're in a tunnel in the Taylor Glacier in the dry valleys here in Antarctica.
I've looked into the future and traveled back in time. I've even been somewhere where time seemed to stand still.
We are highlighting in blue those issues that are within the mandate of the group.
Who are these climate scientists? What do they do? What are they saying? And do they know what they're talking about? Are they searching for the truth, or are they peddling a lie? It so happens that my office in Victoria University, Wellington, is just down the corridor from their Antarctic Research Centre. They told me, if you want to meet climate scientists, go to Antarctica. The place is swarming with them. Thus it was that I found myself aboard a US Air Force C-17 Globemaster in a cargo hold full of scientists, wondering what I'd let myself in for.
Going the very first time to the ice is something that you can't really describe. It's a really once-in-a-lifetime experience. Standing on a sea ice runway in the middle of this huge continent. It's a feeling like landing on the moon, I guess. I mean, I've never been to the moon, obviously, but I could imagine that maybe the astronauts would feel a similar way. But once you're there, you just see the beauty. You see this amazing continent with all its histories, its secrets, and it's right there in front of you. It's truly amazing.
The New Zealanders kindly made room for me at Scott Base.
Around 72 degrees south.
This is the permanent base that supports New Zealand's scientific research in Antarctica. Research that covers the whole spectrum of science, from physics to biology. The base, of course, is named after the leader of one of the very first scientific expeditions to the southern continent.
Scott's expeditions were very much science expeditions, and his team was more than half the composition was scientists, and covering the broad spectrum of science from geology to geography, meteorology, biology. Going to the pole in many ways was the means of raising the funds. It was the sort of carrot to attract funds to carry out a scientific expedition. We're at Scott's hut from his second expedition of 1910 to 13. Their records, everyone compares back to them, I guess, to see how things have changed over time, so it was all important stuff. I admire their fortitude and courage under just incredible conditions. You know, it's hard to imagine the deprivations they went through.
Today, the only people allowed to live and work in Antarctica are scientists and their support staff. I found the variety and ambition of Antarctic science quite staggering, and the common thread linking much of the research was, perhaps not surprisingly, ice.
These are ice platelets, and you know, almost fresh water, and so we think it plays a role in the growth of the sea ice.
Hey, Brent, you ready for the next block?
Ready?
We're looking for microbes that reside in the ice and that may respire the carbon in the ice to form CO2.
Last year's course, looking at the younger part of the geological record, we were able to see a record of advanced and retreat of the ice shelves. And now we're in sediments that are getting up towards 20 million years, 15 to 20 million years, so it's a much older part of the climate story.
The Antarctic Peninsula is a perfect example of a place where sea ice has disappeared, and so have Adelie penguin populations. They really need the sea ice to do well.
Ice, it turns out, is not just frozen water. It's frozen history, climate history. I knew that climate is just average weather, and I noticed that an important daily ritual at Scott Base was the recording of the temperature.
Current temperature at the moment is minus 7.6. The maximum temperature since this time yesterday is minus 6.6. It's about 50 years. It was 1957 that observations started being taken here. They were taken every 4 hours. I'm lucky I only have to do them every day at 9 o'clock. But I'm conscious that I don't want to be the first science technician in 50 years to be hungover from the party last night and miss the observations. And reset this. I better hold on to this properly. I don't want to let go of it and put mercury everywhere. It's easy to do that in winter when you're wearing big gloves. There's a 1 degree change in the mean temperature here at Scott Base over the last 50 years, and that's reasonably significant in terms of change over a short period. In previous parts of history, there's been perhaps a 4 degree change every 1,000 years, so 1 degree over 50 years is quite significant.
So people have been recording the weather in Antarctica for about 50 years. 100 if you include the observations made by Captain Scott's expedition. But on the Evans-Piedmont Glacier, I learnt that snow and ice have been recording the climate for much longer.
Well, girls, pick your weapons. Because snow is an amazing material, as it forms in the atmosphere and falls down to accumulate here, it captures a lot of information on the particular weather of the day, of the month, the year. And as you can see, you see these wonderful structures here in the snow, which represent annual layers. And so by digging the snow pit, we're going back about 40 odd years in time.
When I visited, Nancy Bertler's colleagues were carefully harvesting snow that had fallen over the past few decades, a period when we have records of how the climate was changing.
At the end of the day, what we're measuring is chemistry, is isotopes, and to understand how the climate record is preserved in the snow, we need to have some time of overlap where we can see what the weather did and what the snow tells us about the weather. We use then this knowledge to go back further in time with the ice core records, where we go back many thousands of years, but where we don't have the luxury, of course, of having meteorological observations.
I was intrigued by these ice cores that Nancy had mentioned, and then I was told that there was an American-led team of scientists drilling ice cores up on the vast Antarctic polar ice cap. So I hitched a ride on a logistics flight, which took a mere 2.5 hours to cover the same ground Captain Scott struggled over for 2.5 months. Apparently, this small team was travelling right across the polar plateau, drilling ice cores as they went.
We started about 450 kilometers north of here last year. Only managed to travel the 450 kilometers. Typically, we travel much more than 1,000 in a season. We effectively travel in 3 different groups. The first is that red piston bully, has a crevasse detector on the front. Then the second train will have the kitchen and the accommodations. It's dragging experiments, looking down into the ice. And then the third train is made up of ice cores and additional scientific equipment.
I'm Daniel Dixon. I'm a PhD student with Paul Majewski. We're trying to understand the climate of Antarctica for the last 200 to 1,000 years. And I do this by looking at the chemistry of ice cores.
These are our 2 ice core drills. One recovers about a 3-inch diameter ice core. The other about a 2-inch diameter ice core, and they can go down about 100 to 200 meters, allowing us to go back 200 to about 1,000 years.
The way this drill works is similar to the way you would drill a hole in the wall of your house. But the only difference is our drill bit is hollow, and so while we're drilling, the core is actually captured inside the drill bit. Paul will push the core from this end, and the chips will empty. And here comes the core. And there we have a perfect meter of core.
Well, we understood from the late 1960s, probably until about 15 years ago, or believed, I should say, that Antarctica was a very stable place. Giant, white, cold mass of ice that never changed. In the last 15 to 20 years, we've learned that this place is very, very dynamic. This may be a cold spot, but climatically, it's a real potential hot spot for change.
So overall, we drilled 1,000 meters. That's almost a decade worth of work. So this is our core. on this one. It's not the easiest of jobs. It's a little bit fiddly. We set it onto a continuous smelter, which is pretty much just like a hot plate. And it melts the ice core layer by layer, bakes through time. And as the water is produced, it is pumped by these pumps into these various tubes. And this allows us to do analysis of all sorts of things that are contained in these ice cores. So we're looking for properties of the water that tell us about the temperature. We're looking for dust as an indicator of wind strength, where this air mass might have come from that precipitated the snow. And so by studying how much of these various components is in the ice, we get a feel for what climate was like at the time when the snow fell.
But what really fascinated me was that the ice cores allow us to relate changes in past climate to changes in the composition of the ancient atmosphere.
In the ice cores, there's little bubbles, and those bubbles contain a real sample of the atmosphere through time. We can release that air and measure the greenhouse gases. You could almost say we're taking the DNA of the atmosphere.
Nancy and her colleagues are just one of many scientific groups examining ice cores. I found a lot of the original scientific papers on the web, going back over 30 years. All the cores seem to tell the same story, a regular pattern of warming and cooling as the planet passes in and out of ice ages.
Yeah, so we've got this remarkable record in the ice cores, and we see these very regular but quite dramatic shifts, going from warm to cold, warm to cold, warm to cold. And these are the glacial interglacial cycles happening every 100,000 years.
But what's really striking is the way that carbon dioxide levels show exactly the same pattern as temperature. It's probably the best correlation in any natural data set that I have ever seen.
The greenhouse gases also show the same pattern. So when carbon dioxide goes up, the temperature goes up. Vice versa, when the carbon dioxide goes down, the temperature goes down. And for all intents and purposes, it looks like they're totally locked together in step. And it really is, you know, a remarkable piece of science. It's revolutionised the way we think about the climate system.
This discovery, that going back hundreds of thousands of years, there's a link between carbon dioxide in the atmosphere and temperature, must be one of the most important things to come out of Antarctic science. But to me, this correlation was still not proof of the central claim of climate scientists, that changing levels of CO2 are actually causing the changing temperatures. I realized I needed to know a lot more about what carbon dioxide does in the atmosphere and why it's called a greenhouse gas. It was time to talk to physicists.
We're going to try to go through in this tutorial basically what controls the climate of the Earth.
But I was rather taken aback at what they said.
The question of whether or not greenhouse gases are causing global warming is completely uninteresting to a physicist. Of course they're causing global warming. So
it turns out that the theory of global warming, the greenhouse effect, was all worked out some time ago.
If all we knew was that greenhouse gas levels were going up, and supposing we didn't have any record of temperatures over the past 50 years, we would still expect, as physicists, the world to be warming as a result.
Really, what we're talking about is not so different from the warming effect that you get from adding fiberglass insulation to your house.
So we've got a big, chunky amount of shortwave energy coming in from the sun.
If we want to understand the climate, or in particular the temperature, the surface temperature of a planet, you first have to understand something about the connection between temperature and energy. Temperature is, loosely speaking, a measure of the energy content of something. Something that is hotter actually has more energy inside it. And so in order to determine the temperature, you need to know something about the rate at which energy goes in and the rate at which energy goes out. In 1827, it was recognized that the energy source that maintains the Earth's temperature is not energy coming up from the interior of the planet, but the sunlight that's absorbed. And so if you kept absorbing all this sunlight and you kept accumulating energy, then the planet would just heat up and heat up and heat up. The temperature would grow without bound until we melted. So the other part of the equation that determines the temperature of a planet is the rate at which you lose energy. And here the key insight was that the hotter a body gets, the more rapidly it loses energy. And so you're receiving energy at more or less a fixed rate from the sun, and then the temperature builds up and builds up and builds up. The hotter it gets, the more rapidly you lose energy to space. And then bang, when what goes out equals what comes in, that's your equilibrium temperature.
Though on reflection it's obvious, I was still struck by the fact that to avoid burning up, the Earth must constantly lose energy to space.
Given that outer space is essentially a vacuum, the only way that a planet can lose energy, the only thing that exits from a planet is light radiation, electromagnetic radiation. And light, I mean broadly construed. So there is light that we can't see, infrared.
And you can actually feel the effect of infrared energy from the Earth. If you go out on a clear night in the winter and you hold your hand above the ground, you can actually feel that the bottom of your hand feels warmer than the top. And that's the flux of infrared energy escaping from the Earth. The reason I said it had to be a cold night in winter, because those are some of the few conditions in which you actually do get radiation escaping from the surface of the Earth directly. On most days, under most conditions, the atmosphere is far too thick, far too opaque for this infrared radiation to escape directly to space. And this is the thing people have to understand. The atmosphere looks completely different in the infrared. If we were wearing goggles which only allowed us to see in the wavelengths that the Earth uses to shed energy to space, we wouldn't be able to see very far. We'd barely be able to see 200 yards to the college over there.
Most of the atmosphere is nitrogen and oxygen. I mean, 80% of it is nitrogen. And nitrogen doesn't really absorb infrared radiation very well. It doesn't absorb heat very well at all. So anything like carbon dioxide, which is a different type of molecule, it has a different shape, essentially, is much, much better at absorbing heat, specifically at the wavelengths, the parts of the colors of the spectrum, where the Earth itself is re-emitting that heat. Okay, what I'm going to do is I'm going to puff some carbon dioxide from this fire extinguisher into the beam between the sun and the instrument and see what effect that has on the absorptions. Here we go. We'll see what that does. So here we've got the two spectra that we measured from outside. The black curve underneath is what happened after we puffed the carbon dioxide from the fire extinguisher in. And here you can see this strong absorption feature due to CO2. And this shows why carbon dioxide is such a good greenhouse gas, because it has such strong absorption in the infrared, where the Earth is re-emitting heat from the sun.
But the higher up you go, the more tenuous the atmosphere gets, the thinner it is. So there's less greenhouse gas there, just because there's less gas of any sort. And so there's always some level where the atmosphere finally becomes thin enough that the radiation can escape to space. And that is called a radiating level.
I've been doing this twice a day for the last 40 years.
Do you enjoy doing this?
It's fascinating. You never can tell what you're going to get on your flight, and it's always different.
As you're going up in a balloon, you're in effect rising through the mist and escaping slowly from the greenhouse blanket that envelops the surface of the Earth. And when you get to around 5,000 meters, you've reached that critical altitude where energy can begin to escape to space.
And that level is colder than the ground. because the higher up you go, up to a certain point, the colder it gets. And that is called the radiating temperature of the planet.
Okay, the temperature plot we have here starts at the surface at about 18 degrees. At about 10,000 feet, we go through the freezing level. You can see the temperature decrease up to this point here, which is about 12 kilometres, which is the tropopause. And then I'll be back here at midnight tonight and do it all over again.
That difference between the radiating temperature, which is something you measure from satellites and can confirm, that difference between the radiating temperature and the surface temperature is accounted for by greenhouse gases.
If you looked at the planet from space, it would look as if the planet had a temperature of minus 18 degrees. That's the temperature, in fact, we would have if we had no atmosphere. But in fact, of course, we have a blanket of greenhouse gases surrounding the Earth. What you see from space is the top of that blanket, so to speak, which, just like a real blanket, can be much colder than the bottom. So where we are, underneath this blanket, is a nice, comfortable 15 degrees on average.
No matter how much greenhouse gas we add to the atmosphere, we will not, in the long term, change the radiating temperature of the planet, because the radiating temperature is determined by the requirements of energy balance. So if the Earth is radiating at a temperature of minus 20 Celsius today, in round numbers, then even after adding a lot of carbon dioxide to the atmosphere, it will still, once it comes back into balance, be radiating minus 20. When we add carbon dioxide to the atmosphere, we are not primarily changing the radiating temperature. What we're changing is the radiating altitude.
Now, what happens when we raise greenhouse gas levels is you make this fog thicker and the mist rises slightly. And where you are, energy can no longer escape to space. You have to go a little bit higher for the energy to escape to space.
The more greenhouse gas you stuff in the atmosphere, the higher you have to go before the atmosphere is thin enough to let the infrared radiation escape to space. So that the atmosphere is radiating to space from a higher altitude than it used to be, so that the temperature at the radiating level, which is still, let's say, minus 20, remains at minus 20, but that temperature is occurring higher up. And since the temperature, or the rate of temperature increase as you go deeper in the atmosphere is approximately fixed, but you're starting at that minus 20 from higher up. By the time you extrapolate to the ground, you wind up with a higher temperature. On the average, temperature goes down about 6 degrees with each kilometer that you go up. And so we can ask the question, how much higher do we have to push that level in order to get, say, a 2-degree warming at the surface? Well, to get a 6-degree warming, you would push that radiating level up by 1 kilometer. To get a 2-degree warming at the surface, you only need to push it up about a third that much, which is, in round numbers, 300 meters. It takes relatively little increase in the infrared murkiness of the atmosphere to change the altitude at which infrared escapes to space by a mere 300 meters. And that's part of why the climate is so sensitive to greenhouse gas concentrations.
So the link between temperature and carbon dioxide was basic physics, ideas that have been around for over 100 years. But are global temperatures really rising in the way these ideas would suggest? Working out an average temperature for the whole planet is obviously not a simple matter. But a little bit of research on the internet soon revealed that there are in fact 3 different scientific groups that have undertaken the task. The groups are independent of each other, and their estimates of global average temperatures differ slightly. But overall, they reach very similar conclusions. I went to meet Professor Phil Jones, who leads the British effort, based at the University of East Anglia. Phil's office took me rather by surprise. It was crammed with scientific publications, and there was barely room to film. But Phil seemed quite at home here.
Most of the climate information we have access to, not just for temperature, but other variables too, is collected for weather forecasting purposes. So it's the primary use is weather forecasts. And you can think of climate as a second-hand user of weather data.
Phil has also collected weather data like this, going back in time more than a century.
This is the book with Scott's expedition and others to the Antarctic, 1909 to 1911 period. So it contains all the temperature, pressure, snowfall, other weather measurements that were taken both at the bases along on the coast and on his ill-fated expedition to the South Pole. So this is one of the Russian yearbooks for 1847. And this one contains daily data and monthly data from various places across Russia. And it tells us the temperature and the pressure every hour, the daily rainfall totals. So again, we've gone through these and digitized lots of the data, and all this goes into our database.
There are one or two coolish decades in the second half of the 19th century and one or two slightly warmer decades, but there's no real overall trend in temperature on longer than decade timescales until you get to the 1910s. Then you have a warming of temperatures, quite a dramatic warming from the late 1910s to the middle of the 1940s, which is more marked in the Arctic region than in other regions of the world. And after that time, the temperatures cooled slightly to the late 1970s, and they've warmed very dramatically since. And the top 10 warmest years are all from 97 through to 2008, with the exception of 1999.
The temperature records show that over the past few decades, the region that had warmed fastest on Earth was the Arctic. I wanted to find out what the people who lived there had experienced. So I jumped at the chance to visit northern Norway. Exactly how long the Sami people have been here seems to be a matter of debate.
Sami has been reindeer herders very, very long time. Some scientists say 400 years, and of course it is several thousand of years, not only 400 years. So whole the culture, the identity and so is connected to reindeer husbandry. Of course it is very close, we live very close to the environment, and also it's a way of life to live with all the changes in the environment. And you know, in Arctic you have a lot of changes in the climate. Trees are growing on the tundra. It's bad because trees, they kill lichen. The reindeer don't like it. And of course it also covers more snow when it is wind. So the snow will be very hard.
...35-40 kuldegrader, december, januari, februari. Men nu det nästan regn någon gång.
I asked Ole Henrik about climate, how he feels that this has been, and he feels it's a big change on his. Because earlier it was very common with long periods already in December, January, February, with temperatures between 35 below, 40 below Celsius. And no, it's very, very common with rain in December. In the last 10 years that have really noticed changing.
By now, I felt I'd seen a lot of evidence that the Earth is actually warming, and that rising levels of carbon dioxide are part of the explanation, if not the whole thing. But everything I'd learnt so far was about the past. What about the future? I knew scientists were making predictions about global temperatures at the end of this century and beyond. Could they really be so confident? Two-thirds of the Earth is covered by water. So it's what happens to the oceans that will determine the future of the world's climate.
The ocean stores an enormous amount of heat. In order to warm the planet, we ultimately have to warm the whole ocean. And that to warm the whole ocean is an enormous thing.
So what is happening to the world's oceans? With a slightly sinking stomach, I accepted an invitation to join the RV Tangaroa, New Zealand's deep water research vessel, on a cruise to the Southern Ocean.
I'm sure I'm preaching to the choir here. Anybody who's sailed in the Southern Ocean has felt its turbulence. If we look at any yachtsmen that have sailed around the world yacht races, the big bogey in the race is always the Southern Ocean. Oceanography covers a whole range of disciplines. So you have to have some knowledge of chemistry, you have to have some knowledge of the climate, of the geology, of the biology. So there's a whole range of things. When you go to sea, you have these in the back of your mind. But I do get seasick, and that's the fact of life. But as soon as that ship leaves port, we're in business. Because we're running 24 hours a day, we have one team doing 12 hours, the other team doing the second 12 hours. When we reach the first of our scheduled survey points, then, well, I like to say all hell breaks loose. We take lots of water samples, and so we're constantly recording the depth of the ocean. We're constantly recording the temperature of the ocean surface water.
Temperature is fairly constant down to about 30, 40 metres. Then it slowly starts dropping off. And the deeper we get, the lower the temperature.
We have a range of instruments, current meters, temperature loggers, sediment traps, instruments for measuring carbon dioxide in the water. This is probably close to the 20th time we visited this site.
There's really no other way to get a time series of measurements from the depths of the ocean. So we're just turning it around, replacing the instruments, and we'll be leaving it again now for about another 8 months.
I love my work. I suppose I shouldn't say, but I've been doing this for almost 20 years, and I really enjoy coming out to sea. It's what makes being an academic fun. You cannot do the science without knowing where your samples come from. You can ask people to bring you home samples, but if you don't actually see where things are coming from, it's easy to miss the subtleties in what you're looking at.
The warming, which initially affects the atmosphere and the near-surface ocean, is slowly penetrating down into the ocean depths. The ocean is acting as a brake on the surface warming. It's holding surface temperatures down.
The planet hasn't caught up with what we've already done.
So emissions in the past mean that we're going to see further warming through this century anyway.
So we shouldn't expect the climate change which we've seen so far to be all we're committed to as a result of the greenhouse gas emissions we've made so far. In fact, it's probably, maybe over half, but probably only around 2/3 of what we're committed to.
My time at sea made it clear that predicting the future of the climate was not just a matter of understanding the atmosphere. Somehow, we needed to incorporate what happens in other parts of our world, particularly the oceans. So I arranged to meet some scientists who were trying to do just that, using computers.
We can do the experiment with the Earth only once, but in a computer you can simulate the Earth thousands and thousands of times.
We want to simulate the oceans, the atmosphere, the biosphere, and all the interconnections in between. And that's why it takes so long, even on these powerful computers, weeks and months to project the climate for a couple of 100 years.
Back when this science was relatively young, in the 1980s, they predicted the kind of warming we should expect to be associated with the rate of increase in greenhouse gases that we've observed. And they predicted it to be between 1 and 2/10 of a degree per decade. And that's exactly what we've seen since that time. So, this was, if you like, a 20-year weather forecast, which appears to have been remarkably successful.
The big question the models are designed to answer is how sensitive is the climate to the warming effect, the so-called forcing of increased CO2. The answer the models suggest is that if we double the level of carbon dioxide, the world will warm by 3 degrees Celsius, or thereabouts. But if we continue as we are doing, by the end of the century, carbon dioxide may well be 4 times higher than pre-industrial levels, implying a world 6 Celsius. That's 11 degrees Fahrenheit warmer. But can the models be trusted so far from experience? Have they really got the climate sensitivity right? This is Matt Huber, a paleoclimatologist from Purdue University, Indiana.
A lot of people are skeptical of climate models, and it's very good to be skeptical of them. There's always a question, well, if you kick the model, if you push it towards a warmer world, is the model tending to be overly sensitive to that push? Or you push it a little bit and the model goes crazy and it gets way too warm? Or is it possible that if you push the model, it doesn't budge nearly as much as it should, it just moves a little bit? You can look over the past 100 years and try and infer what the true value of climate sensitivity should be. And right now we don't know whether that value is 1 degree of global climate change per doubling of carbon dioxide concentrations, or 5 degrees of warming per doubling of CO2. And the paleoclimate record is providing a lot of really useful insights into which of those numbers is closer to the truth. Is it 1 or is it 5? So what I've done in my research and what other people have done in my field of research is look at past periods of global warming as a way of understanding the ways in which models produce warmer climates and also the degree to which they reproduce the magnitude and pattern of warming correctly based on comparison with paleoclimate data. So here's the amazing thing. This is the world as it was in the Eocene 50 million years ago. There were crocodiles near the North Pole. And there's also fossils of tortoises and a whole variety of subtropical plants. This was clearly a subtropical swamp environment during the warmest periods in the Eocene, more like the coast of Florida than the North Pole is today.
The fact that the climates have changed so dramatically in the past is the strongest evidence for the reality, the correctness of our understanding of climate sensitivity in terms of principles of energy balance. If you had a situation where the climate just remained rock solid for the past billion years, then you would have a pretty strong argument that there was some stabilizing feedback that just kept the climate from changing very much. Whereas we do know that if you go 55 million years ago, the climate was substantially warmer than it is today. There was no ice essentially anywhere on the planet, no permanent ice. And we know that the only lever you have over climate that can cause that kind of change is a change in the greenhouse gas composition, change in the carbon dioxide. We even know to some extent what the greenhouse gas concentrations were.
So there's a variety of techniques for estimating the past atmospheric carbon dioxide concentrations. But the one that I find the most convincing is actually there's a certain kind of mineral that only forms under high CO2 conditions, and that mineral, naucolite, is actually known to have been forming 50 million years ago and not subsequently after that. If you set the models up with the conditions appropriate for 50 million years ago, including higher greenhouse gas concentrations, the models are significantly warmer than the climates produced by the models are today, but they're not warm enough. And that indicates that the models tend to be not sensitive enough to forcing due to CO2. That's what the paleoclimate record indicates, is that sensitivity is more towards the high end, 4 or 5 degrees of warming per doubling of CO2, as opposed to 1 or 2 degrees.
So if anything, the climate models may underestimate the future pace of global warming. It seems likely that over the next decade or two, climate change will begin to accelerate. To find out what that might mean for the planet, I took one last trip back in time. I found the time machine I needed sitting on the sea ice in the middle of McMurdo Sound in Antarctica. Andrill.
We made a hole 84 metres deep, then we lowered our pipe through the ice shelf and a further 850 metres down to the sea floor. And from there, we drilled back in time 14 million years through sedimentary layers of rock. We got to the bottom of the hole. We had drilled 1,284 metres of core. We bring up these layers core barrel by core barrel, very laborious. All this information is absolutely vital to reconstructing a picture of what our planet looked like at a time which is probably a very good example of where we're heading to.
The rock cores are a treasure trove of information about past conditions in the Ross Sea.
What actually came out of that hole had our eyes out on organ stops. We were just staring at this core and seeing these dramatic changes in environment from full-on glacial conditions, and then just over half a metre of core, wham, you're into green algal blooms. And the characteristics of many of these blooms indicate temperatures were 2 to 3 to 4 degrees warmer than they were today. And we're starting to build a picture of a very different Ross Sea, Antarctica, West Antarctica, during some of these warm periods in the past. It's quite a cautionary tale, if you like, to be able to look back and realise that only under marginally higher values of CO2, these elements are incredibly sensitive. The West Antarctic ice sheet is a very sensitive feature. You don't have to do a lot to destabilise it. And we are doing a lot right now. We just haven't seen the consequence. If the temperatures of the ocean increase by up to 5 degrees, the West Antarctic ice sheet will collapse. It will disappear, and sea level will be at least 5 metres higher, and I guess we'd have to assume Greenland would be gone as well, so 10 metres higher.
Over the next 100 years, we are going to be pushing CO2 up to levels last seen something like 45 or 50 million years ago, when there was no ice at either pole and crocodiles were swimming off the coast of Greenland.
Where we're headed into the future, we have an idea where that may go by looking back in the past. If you look across here 5 million years ago, you'd see no ice in the sea. You'd see not so much ice on the hills. You might see green over there. Going back 15 million years ago, you'd see a whole different biota down here. You'd probably see porpoise and dolphin swimming out there rather than killer whales.
It seems we're on course to take our planet back millions of years. It's unlikely that much of the natural world we know will survive the transition. What will happen to human society is impossible to say.
I look at my kids and I look at the way people behave, and by and large, people are pretty adaptable and pretty resilient. And so I don't worry that we are going to all get killed by this thing. I do worry that our children are not going to thank us for giving them the headache we're going to give them if we carry on the path we're following. Because if we don't get out of this, they will have to. And every decade we postpone doing anything about global warming is another 100 billion tons or so of carbon into the atmosphere, and we're that much closer to the sort of climate where we really can't predict where the warming will stop.
If sensitivity to carbon dioxide variations is something like 4 or 5 degrees per doubling, then that means we actually need to reduce human emissions of carbon dioxide to 0 in the next 50 years, which is a far more radical kind of policy than what most people, most politicians, and most governments are talking about currently.
That's quite important to realize that if we want to stabilize the climate, there's no way around than to aim for zero CO2 emissions in the long term.
Today, the main effort to manage CO2 emissions is the UN Convention on Climate Change.
I hereby declare open the third meeting of the ad hoc working group on long-term cooperative action under the Convention.
Thank you, Chair. Distinguished delegates, the objective of the Convention requires keeping global warming as far as possible below 2 degrees.
It was obvious to me that getting the whole world to agree on CO2 emissions is proving depressingly difficult. But what finally cheered me up was the experience I'd had with climate scientists, learning about their science. Over 3 years, I'd met dozens and dozens of scientists. I was convinced that they had not been lying. There is no hoax. In fact, I was impressed by the breadth of the subject, how carefully the scientists went about collecting their data, scrutinizing all possible sources of error, and how open-minded they were about their conclusions. This was science at its best, and it has given us a great gift, the ability to look into our future and shape it.
The sooner that we begin to reduce our impact on the climate system, the better off we are. That said, I think we have the opportunity for a very, very exciting future. We understand there's a problem, we understand the direction that we're going, and we need fixes that are going to be valuable.
And often when I go and talk to school groups, I come away wondering whether I've just scared them. And I think it's important to tell them, no, don't be afraid. You know, here's something that we're going to get through, but for you kids, yeah, take it seriously. Don't be alarmed or afraid, but join in this effort. You know, become the best scientists or engineers you can, and let's solve this problem.